Okay, it's 7 o'clock, so let's go ahead and get started. Welcome everybody. Good evening. How's everyone doing today? All right, good. Hopefully. So I know that there's some questions on homework 3. Yeah. Okay. So I know there's some questions on the most recent homework. So let's kind of review that. Okay. So I know there's a lot of questions on problem 3. So I want to just go over problem 3 part A, but you want to go over problem 2, and I can do that. Okay. Do you have a specific question on problem 2, or do you just kind of need to get started with it? Okay. So let me help you get started with problem 2. Oh. Okay. So 2C, you don't have H, but you can. So the plot that I gave you right there is X over H. So I want you to put the solution in terms of X over H, and then you can plot it in terms of that. So basically, I don't have it. Oh, I do have it. So if you look at the graph that I gave you on problem 2C. On the y-axis here, we have lambda, right? And on the x-axis, we have x over h, okay? So the graph is from x over h, so that should be your dependent variable, and not x by itself. So you're right, you don't have h, but you do have x over h. So if you can manipulate that equation so that you get everything in terms of just x over h, then you can plot the lambda in terms of that, and that should help you out. Okay, does that make a bit more sense on that? Okay. So like if you look at the posted answer for part D, then you'll see kind of what I mean. So you can see that I never have x by itself. It's always x over h. Yeah. Okay. Okay, and then I noticed there's some questions on problem 3A. So let me get that started for you guys, because that one's actually really tricky. Okay. So problem 3A, we have a rotating cylinder. Okay. So this is spinning. Okay. And so what's going to happen, kind of as we talked about last time in class, that once you start spinning the cylinder and it's kind of reached steady state, then this is basically going to start acting like a solid body. Okay. And so what's going to happen, kind of like we talked about last time, is that the surface of the water is going to turn into a parabola. Okay. Okay. And so it's going to turn like that. And so what I'm asking you to do in this problem is, we're basically going to assume that we're spinning the cylinder so fast that there's going to be a section on the bottom of the cylinder which is going to be exposed. So it's not going to have any chemical that's going to be touching it. So what I want you to do is to basically solve for the area of this exposed part. Okay. And so to do that, it's a little bit tricky, because in the notes, which I have right here, what I gave you was a formula for the pressure for Z, right? So from the notes, we get that if we have solid body rotation, then the curve for the free surface is given by this formula. So we have Z is equal to omega squared r squared all over 8G. Okay. And it's subtracted by some other stuff, but we can assume that that other stuff is going to be 0. So we're going to just ignore that. Okay. Right. So this is the formula for a parabola. Right. So you're certainly going to be using this formula for this problem. But the problem with this formula that we didn't really talk about is we don't know where the origin is going to be. Okay. So we're assuming the pressure difference is 0 because that part of the cylinder, or this curve right here, is going to be atmospheric pressure. So then when atmospheric pressure, then we assume that it's effectively 0 pressure. Yeah. And then and the thing on the bottom is 8G. So G for gravity. Okay. Right, so we don't know where the origin is. So we know that it's going to form a parabolic shape. We just don't know where this guy is. Okay. Okay. And so to actually compute that, we're going to put this in terms of 2 variables. So actually, let me clear the board just to make it a little bit easier to see. Okay. So here we have our cylinder. We have our parabola, which goes down to some imaginary point. Okay. Okay. So I'm going to define 2 heights here. So the first height is going to be from the origin to the bottom of the cylinder. So that's going to be H1. And then the second height is going to be from the origin up to the top of the cylinder, which is H2. Okay. So both of these are unknown. Okay. So we don't know what that is, what they are, because we don't know where the origin is. So basically, we need 2 equations to solve for this. Okay. One of them is pretty simple because we know the height of the cylinder. So if we take H2, let me get a better looking H. H2 minus H1, we know that this is 30 centimeters. Okay. So that's one equation that we can use for that. Okay. So the other equation that we can use is the one that I gave you in the homework document, which is the volume. Okay. So the volume of fluid that's inside this this cylinder is going to be the integral from H1 to H2 of pi big R squared, where big R is the total radius of the cylinder. Okay. Minus little r squared of z dz. Okay. Where little r defines this distance right here. So little r is the distance from the center of the cylinder over to kind of the surface of the water. Okay. So this you can obtain from our previous formula. So remember, our previous formula was this. So we can use this to solve for r squared. So r squared is going to be 8gz all over omega squared. Okay. Where you know basically everything here except for z, which you can plug in. You know the radius of the cylinder, which is big R. It's given to you in the problem. You know pi. And you can actually compute the original volume of water, because from the problem we know that the originally the cylinder is only filled up to 20 centimeters. So the volume is going to be pi big R squared times 20 centimeters. So let me make this a little more clear. So basically, you know everything in this formula, and then when you integrate it, you're going to have H1 and H2 pop out, and then eventually when you do that, that's going to give you your second equation for H1 and H2. Okay, so you combine this with the H2 minus H1 is equal to 30, and that should give you everything you need to solve for H1. Okay. Then once you have H1, oops. Then what you can do is you can solve for the radius. Okay, using this formula right here. Okay, and then once you have the radius at h1, then you just do pi times r squared, and that will give you the area. Okay. Yeah, so it's a tricky problem, I know, but you know, follow these steps, and it should lead you to the solution that I got. Okay. Okay, so I'll save 3b because you know, we haven't gone over that stuff in the lecture, so we're going to cover that stuff today. Okay. So are there any questions on this or just anything else in the class before we get started today? Okay. So I got a couple emails this week just to asking for some additional practice problems, because I know for the stuff that's going to be covered on the second midterm, the practice problems are a little bit sparse from the homeworks. So I'm going to work on that tomorrow. So I'm hoping that before the weekend, I'll give you guys some more example worked out problems that you can look at to help prepare for the exam. But I had some stuff I had to take care of today, but tomorrow I'm more free, so I can work on that. So hopefully by the weekend you'll have some more material to look at. Okay. Okay. So let's continue on. Let's pick up where we left off. Where we left off last time was we're going over the ranking vortex. Okay. So the Rankine vortex, the way it's defined is that it's a combination of our two basic vortex flows. So we have first our solid body. Okay. Right. So the way that it's defined is that we have kind of a core. So inside the core we have a solid body rotation, and then outside the core we have idealized vortex. Okay. So the way that we define it was like this. So we say that u theta of r is given by omega r divided by 2 if little r is less than big R, where big R is the radius of the core. Okay. And then outside the core, we have an idealized flow where our idealized vortex, where our velocity is given by omega a squared over 2r. Okay. So this is, you know, the way that a lot of idealized vortices are modeled or actually produced in practice. Okay. Because the unique thing about the idealized vortex is the fact that we have this 1 over r. Okay. So if we try to evaluate this at r is equal to 0, then this leads to a singularity, because that tells us, you know, according to this formula, that means we have infinite velocity. Okay. So, you know, it's actually not possible in nature to have a perfect idealized vortex, you know, just kind of by itself. So the way that we actually get that behavior is actually through a Rankine vortex, where we have a core which kind of rotates as a solid body, and then outside that core we have the behavior of an idealized vortex. Okay? And kind of like what we mentioned at the end of lecture last time, a Rankine vortex is often used to model a tornado. Okay? And actually, the example problem that we're going to do does just that. Okay. Okay. So let's do an example. Okay. So let's consider a tornado. And then we're going to consider it as a Rankine vortex. Okay. And so we say that the core of the tornado it has a diameter of dc. It also has a pressure at the edge of the core equal to PC. Okay. So if we kind of draw this out, then we say that we have our core that looks like this. Okay. So the diameter of this core is DC, and if we evaluate the pressure here, this is going to be equal to P sub C. Okay. Okay. So because we have a Rankine vortex, inside the core, we're going to have solid body rotation. And then outside the core, we're going to have an idealized vortex. Okay. So we want to compute a few things. Okay. So part A, we're going to compute the vorticity inside the cylinder, or in the tornado. Okay. Next, we're going to compute the circulation. Okay. And then part C, we're going to solve for the pressure distribution. Okay. So we're going to solve for P of R. So that P of R, since we have a Rankine vortex, it's going to have two different zones. So it's going to have a zone inside the core and then a zone outside the core. Okay. All right. Are there any questions on this before we move on? Okay. All right. So let's do part A. So part A, we're looking for the vorticity inside the tornado. Okay. So since the inside of the core of our Rankine vortex is we know that it's going to exhibit solid body rotation, we can use our pressure expression. Okay. So that formula is given by this. So you have P of R is equal to 1 over 8 rho omega squared R squared plus P naught. Okay. Where P naught, we're going to assume that this is the pressure that's far away from the cylinder or far away from the vortex. Okay. So that can represent basic atmospheric pressure. Okay. So if we evaluate this at R is equal to DC over 2, then we know exactly what that pressure is because that's been given to us in the problem. So because in the problem, what they say is that the pressure at the edge of the tornado, at the edge of the core is equal to PC. Okay. So if we evaluate this at DC over 2, then we can set this equal to P sub C. Okay. So gravity force. That's a good question. So in this problem, we're ignoring gravity forces. So we're basically just considering just the radial part. But if you wanted to include the effect of gravity, like go from the top to the bottom, then you would include that. But in this case, we assume that the pressure is PC kind of along the entire vertical column of the core. Yeah, good question. Mm-hmm. Okay. So we have P sub C is equal to 1 over 8 times rho omega squared times DC over 2 squared plus P naught. Okay. So we have everything in this problem, in this expression, so we can solve for omega now. Okay. So if we do that, we get omega squared is equal to 1 over DC squared times 32 PC minus P naught all over rho. Okay. And then we can take the square root of this to get omega. So then square root, we get omega is equal to 1 over d sub c times square root 32 p sub c minus p naught all over rho. Okay. Okay. So we use the information, or we use the fact that we knew the pressure at a specific location in the tornado to solve for the vorticity. Okay. And remember the fact that we have inside the Rankine vortex we have solid body rotation, and whenever we have solid body rotation, then the vorticity is going to be constant inside that solid body. Yeah, what's up? Is the pressure term a denominator? Is the pressure? Oh no, so this is a rho right here. So this is density. Yeah. Yeah, thanks for clarifying. I know with my normal writing on the board, with the whiteboard, it's hard to tell, but with my even crappier writing with the stylus on the iPad, it's even worse. So I got a new stylus because my old stylus broke like literally 2 weeks after I bought it. Stupid piece of crap. So I'm still kind of getting used to this new stylus. So I know my writing's gonna be pretty terrible, but kind of just kind of bear with me for this. Okay. Any questions on this? Okay. Okay, so that was part A. So now let's do part B. So part B, we're going to compute the circulation inside this vortex. Okay. Okay. So the formula for circulation is given by this. So we have gamma is equal to omega dA. Okay. Where basically we're going to be integrating the vorticity over the area of our cylinder. Okay. Okay. So we're going to use our result from part A and plug that in here. Okay. Okay. And then basically just evaluate this integral. Okay. So the nice thing about solid body rotation, just like we mentioned just previously, was that the vorticity is constant inside the solid body. So if vorticity is constant, we can just pull this out of the integral. Okay. Okay, so we get circulation is equal to our constant vorticity times integral dA. Okay. And then when we take the integral of dA, this just turns into area. Okay. Where area, we can compute it based on the diameter. So this is going to be pi over 4 dc squared. Okay. So then we plug in our omega from part A and we multiply by this. Then what we get is circulation is equal to pi over 4 times dc times square root of 32 times p sub c minus p naught all over rho, where rho is still density. Okay. So simple, just kind of plugging in and then kind of evaluating those expressions. Okay. All right. Any questions on part B? Okay. All right. So then now we come to part C. Okay. So part C, what we want is the full pressure distribution both inside the tornado and out. So we're going to use two different equations here. Okay. So the first one is going to be inside the core. Okay, so inside the core, we're going to use the same pressure formula from before. So we have P of R is equal to 1 over 8 rho omega squared R squared plus P naught. Okay. And this is, which is valid for R, which is less than dc over 2. Okay. Okay. Outside the core, we're going to use the formula for pressure for an idealized vortex. So that formula is given by this. We have P of R is equal to minus rho circulation squared over 8 pi squared R squared plus P naught. And this is for R is greater than dc over 2. Okay. So those are formulas we went over from last lecture. Okay. So in parts A and part B, we solved for the vorticity, omega. Okay. And then in part B, we solved for the circulation. Okay. So to solve for the pressure distributions, all we have to do is just plug in. Okay. So first, let's do inside the core. Okay. So we plug in for omega squared, and we work out the math. Then what we get is this. Okay. So we get P naught plus 4 times PC minus P naught times little r squared all over dc squared. Okay. Right. And then outside the core, we plug in for our circulation. We get the following. Okay. We get P of R is equal to P naught minus 1 over 4 PC minus P naught all over dc squared over 2. Okay. Okay. Right. So this is just a just an example to kind of show you these equations of motion. So this kind of has really interesting applications. In particular, I want you to kind of look at this this equation right here. Okay. And so what this equation tells you is that inside the core of a tornado, the pressure is going to increase as you go from the very center of the core to the edge of the core, right? Because we have a function that's a positive, PC minus P naught R squared. Okay. So what this tells you is that actually in the middle of a tornado, because you have a wind that's moving so fast, you actually have an area of extremely low pressure. Okay. So what tends to happen in tornado country, and this is what I've heard, I've never lived there before, is that if a tornado actually hits your house, what's actually more likely to destroy your house is actually the really, really low pressure inside the tornado. And you compare that to, inside your house where if you have all the windows closed, what's going to happen is that your house is going to actually look like it's going to explode because you have high pressure on the inside and then really low pressure on the outside. So actually, the advice that some people give you in, if your house is about to be hit by a tornado, is actually to open up all the windows so that that pressure outside can easily equilibrate with the pressure inside, so you don't have this this huge pressure difference inside. Can you fly inside the tornado? I am not qualified to answer that question, but my guess is no. Right. So the question is, does that work for being near the tornado? Yeah. So actually, because the tornado is basically going to be producing really high velocity wind, and basically, we know from Bernoulli equation that velocity and pressure kind of an inverse relationship. So basically, the faster the wind is going, then the lower the pressure is. So even if you're near the tornado, you can open your windows so you're not scared of kind of pressure, the big pressure difference. the risk that you take is that if you open your windows, the high velocity wind is going to come into your house and basically take out all your belongings out. So it's kind of a risk reward kind of thing. You know, if your house is in the path of a tornado, you don't have that many good options, you know, other than kind of praying. But that's right. I think it'd be pretty difficult to outrun a tornado, but yeah, hopefully you're never in that situation. But that's kind of some neat little trivia, kind of as a result of kind of what we found. All right, any questions on this example before we move on? Okay. So that's it for the basic vortex flows. So the basic vortex flows, what you need to know is basically solid body rotation, idealized vortex, and Rankine vortex, and their associated formulas for pressure and for the curve of the free stream. So now we're going to jump into a little bit more theoretical stuff. So we're going to do one of the central vorticity theorems, which is Kelvin's circulation theorem. Okay. And Kelvin's circulation theorem, I think, you know, fits with the theme of this class quite a bit. Because remember, the theme of this class is viscous flow. So Kelvin's circulation theorem draws that kind of direct connection between, you know, how is vorticity related to viscosity. Okay. So, you know, the name of this theorem is Kelvin's circulation theorem. So let's start with the formula for circulation. So just like we saw in the previous example, the formula for circulation is given by this. Okay. So we have the integral of the vorticity over some area. Right? So in particular, since we're integrating over an area, this is actually a double integral. So we have double integral of vorticity over dA. Okay. And then if we want to write this in terms of the velocity, we know that the vorticity is actually equal to the curl of velocity. So this is going to be equal to the double integral of nabla cross u dA. Okay. Okay. So this form is okay. So you know, this form, you can use it to compute circulation, just like as we saw in the previous example. But sometimes it's a little bit inconvenient to perform an integral over an area like this. So what we can do is, because this integral has kind of a very special form, we can actually convert it to a different kind of integral using a mathematical theorem called Green's theorem. Okay. And in particular, the integral that we're going to be converting it to is a line integral. Okay. So mathematically, it looks like this. Right. So we have our circulation is equal to the double integral of the curl of velocity dA. Okay. Let me clean that up a little bit. Okay. And so according to Green's theorem, another way that we can compute this is that we can take the line integral, and I'm going to add a circle there to basically tell us we're going to do a line integral over a closed curve of u dot product with dx. Okay. So let me show you kind of visually kind of what this means. Okay. So what Green's theorem states is that, you know, if we perform this integral and say that we have some closed region like this, okay. So basically what we're doing on the left integral was we're integrating the vorticity over this entire region. Okay. Another way that we can do it is we can take the same region And instead of integrating over the entire area, what we can do is basically just walk around the boundary. Okay. And then by walking around the boundary, what we're integrating is, instead of the vorticity, we're integrating the dot product of u dot with dx, where dx is the tangent to our curve. Okay. Okay. So what Green's theorem states is that we are taking the dot product of u, where we have some velocity field that's kind of around this, and we're dot producting it with taking a dot product around that curve. Okay? So intuitively, the way that you can kind of think of this, and the reason that these two are equivalent, is that on the left, what you can think about is, since we're integrating the vorticity over the area, another way to think of the integral is that it's kind of a summation operation. So basically what we're doing is we're adding up kind of all the kind of tiny contributions of vorticity over this entire area. Okay. So it's kind of like a sum of all the tiny contributions of vorticity. And then we can say that that's equivalent to the right scenario because, we're integrating the velocity, but we're integrating the velocity as its dot product, as well as, as it aligns with this closed curve that goes around our surface. Okay? And the thing about this closed curve is that it goes around in a circle, right? So it's kind of an awkward circle, but eventually, you're going to make kind of a full rotation around your original domain. So by taking the dot product between the velocity and that closed curve, you're kind of also computing, how much the velocity is circulating around your domain. Okay. So Green's theorem basically says that these two expressions are equivalent. Okay? So that's kind of like the very kind of physical, way to explain Green's theorem. But of course, there's a rigorous mathematical proof. But we're not going to go through that. But basically, the point is, what I want to make is that another way to compute circulation is with this kind of second formula here, and that's going to kind of form the basis of Kelvin's circulation theorem. Okay. All right. Any questions on Green's theorem before we kind of start getting into the meat of Kelvin's circulation theorem? Okay. Okay. So now that we have that definition squared away, we can kind of go and state what Kelvin's circulation theorem says. So what Kelvin's circulation theorem says is that for a fluid, with no viscosity, conservative body forces, and is barotropic, okay. Where barotropic, what that means is that the density is a function of pressure only. Okay. So if all those conditions are met, then what Kelvin's circulation theorem says is that the circulation around a closed curve is constant. Okay. Or mathematically, the way that we can express this is that we can take the material derivative of the circulation, and that is going to be equal to 0. Okay. So if you have a fluid which satisfies all these conditions, no viscosity, conservative body forces, and is barotropic, then the circulation is going to be constant. So the last two are usually pretty easy to satisfy. So usually the only body force that a fluid experiences is gravity, and that's conservative. And a lot of times, the barotropic assumption is valid. So the only one that we should examine is this kind of no viscosity. So if we kind of work through the math of this, we can kind of see what effect viscosity has on the vorticity. Okay, so let's start working through the derivation. So let's actually evaluate this. Okay, so if we take the material derivative of the circulation, that's the same thing as this. Okay, so if we use the Green's theorem formula that we had before, we can say that this is equal to the material derivative of the integral of u dot dx. Okay, so then if we use the basically the chain rule, we can set this as equal to of the material derivative of velocity dt dotted with dx plus the material or the line integral of u times the material derivative of dx. Okay. And so what we're going to do is we're going to take this expression here and plug in Navier-Stokes. And then see if this equation here is true. So if we plug in Navier-Stokes for that and we evaluate this this line integral here, then we should get 0 given all of those conditions that we set up there were true. Okay. Okay. Any questions on this before I wipe the board? Okay. Okay, so let's work on the first integral first. So let's plug in Navier-Stokes into that, the material derivative of velocity. Okay. So let's evaluate this guy. So this. Okay. So we have the integral of the material derivative of u dotted with dx. So if we plug in Navier-Stokes, then we get the following expression. So we have the line integral of -1 over rho gradient of p dx plus the line integral of g dx plus the line integral of, where'd I go, of the viscosity times the Laplacian of u dx. Okay. Okay, so let's start working on these terms. So let's start with the pressure integral here. Okay. So that's our pressure term from Navier-Stokes. We have 1 over the density times the gradient of pressure. Okay. So let me rewrite pressure into a different form. Okay. So another way to write the pressure gradient is that we can take the derivative of pressure divided by the dx with an arrow over it, because by taking the gradient of pressure, we produce a vector. Okay, and that's kind of another way to do this. So if we multiply that by another dx, okay, then this dx, or this dx comes from right here. This dx is going to cancel out with that. Okay, so then that integral becomes the closed integral of -1 over rho times dp, okay, because the dx's cancel out. Okay? And so what we're integrating basically is the pressure, which is a scalar field, over a closed curve. Okay? So the the properties of a closed line integral is that we start and end at the same place. We're just going around in a circle. So the integral of this is going to be 1 over rho times p at the end minus p at the start. Okay. But since we're starting and ending at the same place, because this is a closed integral, okay, since we're starting and ending at the same place, this is going to be equal to 0 because Pn minus P start, Pn and P start are the same thing. So that's just going to be 0. Okay. Right. So that's this entire first integral is going to be 0. Okay. So in a similar way, since gravity is a constant, we can pull that out of the integral. We just have the closed line integral of dx, where again, we're starting and ending at the same place. So this is going to be equal to 0 too. Okay, so that's going to be gone. So then the only integral we're left with is the line integral of the viscosity times the Laplacian of u dot product with dx. So that integral is actually pretty hard, so we're not going to worry about that because that's that's going to be our viscosity term that we're going to examine later. Okay, so that's the first integral that comes out. So then the next integral is this guy. So we have the line integral of u dotted with d dt of dx. Okay. So this is the second integral that came out of taking the material derivative of circulation. Okay. So we have the material derivative of dx here, where dx, remember, that's a position vector. The derivative of position is always just going to be velocity. So this is going to be integral of u du. Okay. So by taking the kind of the reverse chain rule here, this is going to be equal to 1/2 du squared. Okay. Right. And so by doing kind of the same thing that we did for the pressure, it's going to be equal to 1/2 u end squared minus u start squared. Okay. And since we're starting and ending at the same place, we know that u end squared minus u start squared are going to be the same. So by taking their difference, we also get 0. Okay. Right. Any questions on kind of how we evaluated these integrals? Okay. So we're basically done with the derivation. So we saw that when we apply the material derivative to the circulation, the majority of the terms cancel out. The only term that didn't cancel out is our viscosity term. Okay. So let's kind of sum that up. So remember where we started. We started by taking the material derivative of the circulation. Okay. And then according to our derivation, this is going to be equal to nu times the Laplacian of velocity times dx. Okay. Right. So the only way for, in order for Kelvin circulation to be true, remember Kelvin's circulation theorem says that d gamma dt is equal to 0. So the only way for this to be true is if viscosity is also equal to 0, right? And if you remember, one of the conditions for Kelvin's circulation theorem was that the viscosity was 0. Okay, so our derivation kind of matches up with that. Okay. Okay. So then, what does this mean? Okay. So what this means is that if you have a flow where viscosity is relevant, then what's going to happen is that that viscosity is actually going to produce and or destroy vorticity. Okay. Because from what we see from the equation above, that the material derivative, which kind of represents kind of the total rate of change in a Lagrangian sense of the circulation, that rate of change is equal to something that has to do with viscosity. So viscosity can either destroy or generate vorticity. Okay? And so how does this happen? Okay? So let's draw kind of a flow that we're kind of familiar with. So let's draw a boundary layer flow. Okay. So let's say that we have a plate. So let's say we have kind of the Blasius solution here, and we have our boundary layer that goes kind of up like that. Okay. So we have a free stream velocity. And we know that inside the boundary layer, we're going to have a parabolic looking profile. Okay. Okay. So we have u of y that looks like that. Okay. And then inside here, let me draw a rectangle. Okay. So let's say that red rectangle there represents some parcel of fluid. Okay. And so because we're we're inside the boundary layer, what's going to happen to this rectangle is that the top layer of the rectangle is moving at a faster velocity than the bottom. Okay. So if the top of this rectangle is moving faster than the bottom, then what's going to happen is that, if we look at the same rectangle over here, then what's going to happen is that since the top is moving faster, then the rectangle is going to rotate a little bit. Okay, so it might look like something like that. Not exactly like that, but if there's going to be some rotation. Okay. Okay. So whenever you have a kind of a gradient of velocity like that, where you have kind of a sharp gradient, then that kind of necessarily produces some vorticity because you have kind of different layers of fluid which are moving at different velocities. So when you have that kind of difference in velocities, it's going to cause the fluid elements to kind of rotate a little bit. Okay? And remember, the reason why we have this gradient of velocity here is because here at the wall, we have our famous no-slip condition. Okay? Where because of the velocity or the viscosity that the fluid has to stick to any solid surface. So because the velocity has to equal 0 here, then by the top of the boundary layer, it has to come back to the free stream. We have this very kind of sharp gradient of velocity inside here. Okay. And so because of the presence of these velocity gradients, then that's going to create vorticity, right? Because vorticity, remember, is nothing more than just any kind of rotation of flow. So whenever you have velocity gradients due to viscosity, that's going to cause some rotation. And because we're inducing some rotation, that's going to produce vorticity and it's going to produce circulation. Okay. So without vorticity, basically the boundary layer wouldn't exist and we wouldn't have any velocity variation. So in that case, Kelvin's circulation theorem would be true because we wouldn't have, there'd be no way for us to produce any rotation of fluid elements inside our flow because there's no velocity gradients to do that. Okay. Any questions on that? Okay. So that's Kelvin, and he has his circulation theorem. So there's another guy named Helmholtz, where he said, not fair. If you have a circulation theorem, then I want one too. So he has his vortex theorem. So this is called Helmholtz vortex theorems. Okay. And actually, you know, Helmholtz kind of based his work kind of around what Kelvin did. So these theorems actually came as a result of Kelvin's work. So we won't go through the derivation of these, but I'll just mostly state them. So Helmholtz basically defined a lot of rules regarding vortex lines and vortex tubes. So if you remember that from Monday, that was kind of a way to kind of visualize vorticity. Okay? So what Helmholtz says is that vortex lines, if you have them inside a fluid, they're going to move with your fluid. Okay. Right. So that's this first theorem. So the second theorem is that the strength of a vortex tube is going to be constant along its length. And so if you remember kind of our definition of vortex tubes from last time, where vortex tubes define kind of a localized space of constant, or not constant, but of vorticity, where you know, the lateral surfaces of the tube, no vortex line can either enter or leave the lateral surfaces. So it makes sense that the strength of vortex tube, which is defined by its circulation, it's constant along that tube. So kind of in the same way, you can think of a pipe flow. So if you have flow that's in a pipe, then there's no fluid that can either pierce or enter the pipe. So the flow rate along that tube should always be constant. So that's kind of this is kind of the vortex kind of version of that. Okay. So the next one is that a vortex line or vortex tube cannot end within a fluid. Okay. So it must either end at some solid boundary, or it must form a closed loop. Okay. So if you have some fluid like this and you have some vortex line, then you know your vortex line cannot kind of spontaneously end at some location like this. So if you have some kind of solid boundary, then the vortex line has to basically go all the way there. Okay. So there's kind of a very long derivation for that. So we're not going to go through it, but that's just kind of something that's kind of good to know. Okay. And the last one also involves vortex tubes. So the strength of a vortex tube is going to be constant with time. Okay. And one thing that I should mention about Helmholtz vortex theorems is that because they're based on Kelvin's circulation theorem, then the same assumptions apply. So we're going to assume that the fluid has no viscosity, and that the body forces are conservative, and that the fluid is barotropic. Okay. So think of Helmholtz vortex theorems as kind of an extension off of Kelvin's circulation theorem. Okay. All right. Any questions on this? Right, so the question is, will Helmholtz or tornado equations be on the midterm? So vorticity will be a topic on the midterm, but in terms of theory, you know, Kelvin and Helmholtz, those are more theory stuff. So expect something about that on the short answer. But for the basic vortex flows where we did an example and we did you're doing a problem for that in the homework, then you can expect a problem like that on the midterm too. Mm-hmm. Right. Any questions on this before we get to the vorticity equation? Okay. Okay. So now let's go over the vorticity equation. Okay. So the vorticity equation is kind of the analogous thing to Navier-Stokes. So remember, when we're solving, fluid problems and we're solving for the velocity, Navier-Stokes is kind of our bread and butter equation that we always start with in order to solve for the velocity. So we start with conservation of mass and conservation of momentum with Navier-Stokes. So there's kind of an equivalent thing for vorticity, and it's called the vorticity equation, which will basically allow us, if we can solve this equation, then it basically allows us to solve for the spatial and the temporal evolution of vorticity, okay? At least in theory. So to obtain the vorticity equation, the starting point is actually Navier-Stokes. So Navier-Stokes is actually the starting point for a lot of things in fluid mechanics. But what we're going to do to Navier-Stokes is we're going to take the curl. Okay. Okay. So to take the curl, we're going to take our Nabel operator and cross product it with all of Navier-Stokes. Okay. Okay, so Navier-Stokes, we have our unsteady term. We have our convective term. We have our pressure term. We also have our gravity term. And then we also have our viscous term. Okay. So I'll spare you guys all the gory details of doing this derivation. Okay. But one thing that I will say is that when you take the curl of this equation, what tends to happen, just like we saw in Kelvin's circulation theorem, is that the pressure and the gravity actually go away. Okay. So intuitively, the reason for this is if you think about it, the curl is kind of a way to talk about the kind of the rotation that occurs inside a fluid. Okay. So if you think about the pressure forces and the gravity forces that act on some element of some parcel of fluid, okay, what tends to happen with the pressure and the gravity is that they always act through the centroid of the element. Okay. Okay. So when you have a force that acts to the centroid of an object, there's actually no way for it to produce any rotation. Okay. So we saw that in Kelvin's circulation theorem. So this is we see the same thing here. So when we take the curl, those terms will go away. So you can definitely show that mathematically, but I think this is kind of an easier, kind of more intuitive way to say that. Okay? So after you kind of go through all the really gory derivations, you end up with the following equation. Okay, so we get you get the material derivative of vorticity, so you get d omega dt, okay, where that's a vector, plus this new term, which I'll explain a little bit. Okay, actually this should be an equal sign, sorry. Plus our viscous term. Okay. Right. So this is our material derivative. So this is our total rate of change of vorticity. Okay. This term right here, this is familiar. So if we think back to when we did unsteady Navier-Stokes, then this represents kind of the viscous diffusion of vorticity. Okay. So you can see viscosity actually kind of has a dual effect on vorticity. So it can both produce vorticity by inducing velocity gradients, but once you have vorticity there, it can actually diffuse it throughout the rest of the fluid, kind of in the exact same way that the viscosity can diffuse momentum. So viscosity is kind of a busy guy. It does kind of a lot of stuff. Okay. And this term right here, this is kind of new. So what this term represents here is what's called stretching or tilting of vortex lines. Okay. So, so this is the vorticity equation. So this is kind of the equation that governs the evolution of vorticity in a fluid. So theoretically, you can solve this just like you solved Navier-Stokes. But in truth, this equation is usually not that practical because what tends to be really difficult about vorticity is determining the boundary conditions. So for velocity, it's usually pretty simple to determine the boundary conditions, but vorticity, it's really, really hard. So this equation is not really used that much in practice, but it's kind of used, in theory. Okay. So in particular, let's talk about this kind of middle term a bit. Okay. So we said that this term represents the stretching and the tilting of vortex lines. So what does that really mean? So what tends to happen is that when you have some three-dimensional effects, so things like if you have a rotating coordinate axes, or you have things like Coriolis force, then that can affect your vorticity. So all of those kind of extra effects that can happen to vortex lines due to things like rotating frames, they're kind of encapsulated in this term. But we won't really see it that much in this class because what this term here is, it's purely a three-dimensional effect. So if you're in 2D, then you don't see this effect at all. Okay. So in order to get any stretching or tilting of vortex lines, you need kind of really complex interactions between the flow and the vorticity that can only really happen in 3 dimensions. So we'll kind of leave it at there. So we can definitely dive into that term and see what that means kind of in more detail. But I think for this class, this is kind of good enough. So for the homework problem 3B, what I want you to do is you're not going to solve the vorticity equation, but I'm giving you basically a solution to it, and I want you to basically plug in plug that solution into the vorticity equation, and then just to verify that it's a solution. Okay. Any questions on this? Okay. So one last thing that we'll go over is called the Biot-Savart Law. Okay. Or in other words, this law governs the velocity that's induced by vorticity. Okay. And the key word here is induced. Okay. So you might have encountered the Biot-Savart law before. If you think back kind of to the many years before when you took kind of general physics, kind of the way that it's presented is actually, you know, a lot of people experience Biot-Savart kind of within the context of electromagnetism. So let's kind of think back to those days just to kind of motivate this. So if you think of electromagnetism, one thing that's common is that you have you know, an electric wire, okay? And in this electric wire you have some current flowing through it. Okay? So I here represents the current flowing through the wire. Okay. And so what you hopefully will remember from physics, or not, because I definitely forgot, is that if you have an electric current that's going through a cylindrical you know, path like that, then what tends to happen is that if you consider some point P that's you know, away from the current, what the current will induce is it'll induce a magnetic field at P. Okay. So if you remember kind of from the Biot-Savart Law, you know, maybe not the mathematics, but just kind of the intuition behind it. If you have some current that's coming through here, what tends to happen is that the current is producing some magnetic field that's kind of rotating around that current. Okay. So let's kind of take this analogy and let's apply it to fluids. So instead of a line of current, let's say that we have a line of vorticity. Okay. And so what we can say is that if we have some vorticity or vortex line that goes in a curve like this, and we know that what that vorticity is, what we can say is that that vorticity is going to induce a velocity at some point P. Okay? Because just like the current that's going through the wire, the vorticity is nothing more than just kind of rotating velocity around it. Okay? So the rotation of the velocity around it is going to induce some velocity at P. Okay. So if you actually kind of work through the mathematics, which we're not going to do, you should see that they're exactly the same. So the formulas that you use back in your introductory physics for Biot-Savart for a current and magnetic field, if you substitute vorticity in for current and you substitute velocity in for magnetic field, you'll see that the mathematics are exactly the same. It's just there's some constants that might be kind of slightly different from each other because one is electromagnetism, the other is fluid mechanics. Okay. So I just want to introduce that idea to you, just because it's kind of a cool thing and kind of hopefully it's kind of a hit of nostalgia for you, coming back to intro to physics. Okay, and with that we've reached the end of our vorticity unit. Okay? So after today, you know, there's this is kind of the last thing that's going to be on the next midterm. So the next midterm is going to consist of lubrication theory, boundary layers, and vorticity. Okay. So again, the study guide is on titanium, so definitely check that out. Okay? And so we're out of time, so I won't keep you guys anymore. So I hope you guys have a great weekend. Please stay safe, please stay healthy, and I will see you guys on Monday. And I'll stick around for a few minutes if you guys want to ask some more questions. Problem 3A, were you here at the beginning of lecture today? Okay. So I went over kind of problem 3A in detail at the beginning of the lecture. So once the lecture is recorded, then I'll upload it to YouTube and you can check that one out. Okay. Okay. Problems on 2C. Okay, so let me just answer Lewis's question first. So the midterm is on April 20th, so that's, yes. So the midterm is going to be April 20th. So again, I'm going to upload the midterm at 7 p.m. that day, and then you'll have 24 hours to complete it, to upload it. Yeah. Yeah, no problem. Part C. Okay, let me take a look. Right. So the so problem 2C is actually the same as the question that we answered. You asked in that email before. So you solve it for the same way. So once you have the momentum thickness in part B, then what you're going to do is you're going to plug that into the formula for lambda. Right. So the formula for lambda from Thwaites method is going to be theta squared all over nu times d ue dx. Okay. So you got theta squared. This is from part B. This is just the viscosity, so it's just a constant. Okay. And then due dx, this is you get this from taking the derivative of part A. Okay. Because in part A you solve for ue of x, and then you just need to take the derivative. So once you have all these things, you plug it into this formula here, and then you get a function for lambda, and then you basically evaluate it the same as the as that example. Mm-hmm. Yeah, you end up with something pretty nasty. So that's why I said, you know, kind of the easier way to kind of determine if it's going to separate is to plot that within MATLAB. Because if you try to work with that equation kind of analytically, it is a mess. Yeah. Mm-hmm. Yeah, there was a typo in the original homework, so it's you're right. There should be an X in the numerator, so it's not a 2. So I uploaded an updated version on Titanium, but I think I forgot to send an announcement. But you're right, so it should be an X on that numerator. Mm-hmm. Yeah, sorry about that. All right, so 2C getting that in terms of X over H. So let me get my solution, and then let me take a look. Okay. Okay, so 2C. All right, let's see. What would be a good place to do? So when you plug in for theta, and you plug in for due dx, then you get the following. So you get lambda is equal to 1 over nu times 0.45 nu all over 48 q times h to the 4th. Right. Yes, yeah. So if you plot it and you get and you reach a lambda is equal to negative 0.09 at x over h is less than 1, then you're not going to separate. Yeah. Mm-hmm. Let's see, and this is, so that's a 4. It's not that much better. We have x squared plus h squared squared times x squared plus 4h squared. Okay, and all this is multiplied by 2q over h over x squared plus h squared minus 4q x squared over x squared plus h squared squared. Okay. So then a bunch of terms are going to cancel out. So that's going to cancel out with that. That cancels out with that. And then after you perform some more steps, then you get lambda is equal to 0.45 all over 48 h to the fourth times x squared plus 4h squared times 2h squared minus 2x squared. Right? Do you guys get this for 2c? Oh, okay. Is it pretty different? Oh, John, I think that's right. But I left it in terms of 0.45 over 48. So I think if you evaluate that, then you get 0.01876. Let me just verify that. 0.45 divided by 48. Oh, so we're off by a factor of 2. Oh, the 2 comes from here. Yeah, so we got the same thing. It's just the I kept the 2 inside here. So if you bring that 2 outside, then you have 0.49 or 0.9 over 48 h to the fourth times x squared plus 4h squared times h squared minus x squared. And then this 0.49 or 0.9 divided by 48, this is equal to 0.01875. So yeah, it's we got the same thing. It's just the yeah. I tend to be lazy because I don't have my calculator on hand all the time, so I just leave things in terms of the variables. Yep. Yeah. So in this case, you don't have to solve for x. So let me kind of show you what I did for this. Okay. Let's see. Let me clear up here. This eraser is so crappy. That's why I don't like using it. Okay, so going based off that equation there. So so since we don't have x, what I wanted you guys to do was kind of put this in terms of h over x. Okay. So we have this h to the fourth that's kind of floating out here. So let's distribute that through. Okay, so we have lambda is equal to 0.9 divided by 48 times x squared plus 4h squared divided by h squared times h squared minus x squared all over h squared. Okay. So all I did was I took that h to the fourth that was out here out in front, and I divided through each of those terms. Okay. So we get lambda is equal to 0.9 divided by 48 times x squared over h squared plus 4 times 1 minus x squared over h squared. Okay. And so this formula right here is in terms of x over h. So you can see that there's no x by itself, and you can just directly plot this within MATLAB. Graph relating solution C and solution D. So C, so in C, you would just plot this, or you would just kind of throw this in MATLAB or Excel, and you would produce that plot. Okay. Let me see in part D. let me see here. Right, the pressure gradient. Let me see. So, okay. So for the pressure gradient, you use this formula here. So the pressure gradient is going to be, oh, shoot. So the pressure gradient is 1 over rho times the pressure gradient is equal to minus UE dUE dx. Okay. So you multiply both sides by rho, you get dP dx is equal to minus rho UE dUE dx. Okay. So you got UE from part A. Okay. So you can plug into those expressions there. Okay. And I have it down here. So then if you plug in the solution for A, you get dP dx is equal to minus rho times, let's see, 2q x over x squared plus h squared times the gradient, which is 2q over x squared plus h squared minus 4q x squared all over x squared plus h squared squared. Okay. And so for here, you would basically kind of work through the algebra and kind of put it in the same form that we did in the previous one, where it's everything in terms of x over h instead of x. And then you would make the same plot where you would plot x over h, and then this is dP dx. Okay. And then what I want you to look for in this is that, you know, based on your solution from C, where in your solution from C, you find a location where lambda is equal to minus 0.09. Okay. What I want you to find from the pressure gradient is that is your pressure gradient going to be positive, or is it going to be negative at that location? Right. So if the dP dx is going to be positive, then you know we have an adverse pressure gradient. Okay. So remember we learned from the week prior that an adverse pressure gradient will encourage boundary layer separation. But if dP dx is negative, then we have a favorable one. Okay. So for a favorable pressure gradient, remember we don't have any boundary layer separation. So what I want you to do is, like for part C, is that if you did find boundary layer separation, you should see an adverse pressure gradient in the same location. But if you don't see any boundary layer separation, then the pressure gradient should be favorable. So that's kind of what I wanted you guys to relate kind of in between the two. I get a parabola, half of it is pressure and the other half is boundary layer. I'm not quite sure what you mean by that. If you graph them in the same graph, okay. You get pressure. Ah, okay. Yeah. So the shape of the pressure gradient is you know, I'm more interested in kind of just the point at which you find a separation. So I'm just looking if it's either positive or greater than 0 or less than 0. That's kind of the only thing that I'm looking at. Yeah. Yeah. So I'm not looking for a specific curve. Yeah. So I didn't post the curve for part D. I just posted the solution. But yeah, you should see I'm just looking either positive or negative for that. Okay. So the solution for part D, so the typo was only in just me inputting the solution into MS Word, but in my work I used the correct solution there. So part D should be correct. Mm-hmm. All right, cool. Good night. Yeah, good night, guys. Have a good weekend. Okay, so if there's no more questions, I'm going to end the meeting, and then the recording for this will be up on YouTube either by tonight or early tomorrow morning. Okay. All right, see you, everybody.